Have you ever wondered if you could see a black hole? I mean, really see it? What if I told you the answer is both no and yes, and the yes part is way cooler than you could ever imagine? Stick with me, because today we're going on a cosmic journey to find out how we can stare into the abyss and what it stares back with. And hey, if you love exploring the biggest mysteries of the universe, do me a huge favor and hit that subscribe button and ring the bell so you don't miss our next adventure. So, let's get the obvious out of the way first. Can you see a black hole in the traditional sense, like you see a star or a planet? The answer is a hard no. The very definition of a black hole is an object with gravity so intense that nothing, not even light, can escape its grasp once it crosses a boundary called the event horizon. Think of it as the ultimate one-way street in the universe. If light can't escape from it to travel to our eyes or our telescopes, then by definition, the black hole itself is perfectly black. It's an invisible cosmic monster, a true void in space-time. It doesn't emit light, it doesn't reflect light, it's just nothingness. Trying to see a black hole directly is like trying to see a perfectly black cat in a pitch-black room with your eyes closed. It's just not going to happen. But here's where things get really interesting. Just because we can't see the black hole itself doesn't mean we can't see the absolute chaos it creates around it. Black holes are the messiest eaters in the universe, and it's this cosmic mess that gives them away. Imagine a supermassive black hole sitting at the center of a galaxy. It's surrounded by a massive swirling disk of gas, dust, and a few unlucky stars that have wandered too close. This swirling vortex is called an accretion disk. Now, the material in this disk isn't just gently circling the drain, it's moving at mind-boggling speeds, close to the speed of light. As all this gas and dust gets whipped around, the particles rub against each other, creating an insane amount of friction. And what does friction create? Heat. An unbelievable amount of heat. We're talking millions, even billions of degrees. Anything this hot glows incredibly brightly. So, while the black hole itself is dark, the accretion disk surrounding it can outshine all the stars in its host galaxy combined. It shines across the entire electromagnetic spectrum, from radio waves all the way up to incredibly energetic X-rays and gamma rays. So, what we see is not the black hole, but its glowing, superheated dinner plate. It's a spectacular, indirect way of confirming something is there. And this isn't just theory. We've seen these accretion disks. Telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory have captured stunning images of these blazing disks of matter with a telltale patch of darkness right in the center where the black hole should be. It's like seeing the shadow of a ghost. You can't see the ghost, but you see the effect it has on the world around it. But wait, there's more. Sometimes not all the material in the accretion disk falls into the black hole. Due to incredibly complex magnetic fields generated by the spinning black hole and the disk, a portion of this superheated matter gets funneled away from the poles of the black hole. It's then blasted out into space in two colossal, focused beams called relativistic jets. These jets are truly epic. They can stretch for hundreds of thousands, even millions of light years into space, far beyond the boundaries of their own galaxy. And just like the accretion disk, the material within these jets is so hot and moving so fast that it glows brightly, particularly in radio waves. So, radio telescopes can map out these enormous structures, which act like giant cosmic lighthouses, pointing right back to the supermassive black hole that launched them. Again, we're not seeing the black hole, but we're seeing its powerful galaxy-spanning signature. Another fascinating way we can see a black hole's influence is through something Einstein predicted over a century ago: gravitational lensing. According to his theory of general relativity, massive objects bend the fabric of space-time around them. Light, which normally travels in a straight line, has to follow these curves. A black hole, being the most massive, compact object imaginable, creates a profound warp in space-time. So, if a star or a galaxy is located directly behind a black hole from our point of view, the light from that distant object gets bent and distorted as it passes around the black hole. This can create some bizarre and beautiful effects. We might see multiple images of the same distant star, or the star's light might be smeared into a perfect ring, known as an Einstein ring. By observing these gravitational lensing effects and measuring how much the light is bent, astronomers can calculate the mass of the object doing the bending. If the mass is enormous and concentrated in a tiny dark area, That's a dead giveaway for a black hole. It's like using the universe itself as a giant lens to detect the invisible. But perhaps the most direct way we've ever seen a black hole is through the sound of space-time itself. In 2015, the LIGO and Virgo collaborations made history by detecting gravitational waves for the first time. What did they detect? They detected the ripples in the fabric of space-time created by two massive black holes spiraling into each other and merging a billion light-years away. It was a chirp that crescendoed in frequency as the black holes got closer and faster, before abruptly stopping at the moment of their cataclysmic merger. This was not seeing with light, it was hearing the universe with gravity. For the first time, we had direct, unambiguous proof of black holes existing and behaving exactly as Einstein's theories predicted. Since then, we've detected many more of these mergers, opening up a whole new field of gravitational wave astronomy. We can now listen to the cosmic symphony of black holes colliding across the universe. Now, let's talk about the Holy Grail, the moment humanity finally saw the unseeable. I'm talking about the first ever image of a black hole's shadow, captured by the Event Horizon Telescope collaboration and released in 2019. This wasn't a photograph in the traditional sense. The Event Horizon Telescope, or EHT, isn't a single telescope. It's a global network of radio telescopes, all synchronized and working together, effectively creating a virtual telescope the size of planet Earth. This incredible resolution was needed to see something as small and as far away as the supermassive black hole at the center of the M87 galaxy, which is 55 million light-years away. After years of observations and painstakingly combining petabytes of data, the EHT team produced the iconic image, a fuzzy, fiery orange donut. What are we looking at? We're seeing the glowing superheated gas of the accretion disk swirling around the black hole. But critically, in the center of that ring of light, there is a dark patch. That dark patch is the shadow of the black hole. This shadow is an area about 2.5 times larger than the event horizon itself. It's the region where light gets so bent by the black hole's gravity that it gets captured, creating a sphere of darkness against the bright background of the accretion disk. It's the ultimate silhouette. We are literally seeing the point of no return. We're seeing the edge of the abyss. This image was a monumental achievement, a direct visual confirmation of a black hole's existence and a stunning validation of Einstein's theory of general relativity under the most extreme conditions imaginable. And they did it again. In 2022, the EHT team released an image of the supermassive black hole at the center of our own galaxy, the Milky Way. This one is called Sagittarius A star. It was a much more difficult target to image because it's much smaller than M87's black hole, and the gas swirling around it moves much faster, meaning the image changes in minutes, not days. But they succeeded. Once again, we saw a ring of glowing matter surrounding a central darkness to black hole's shadow. We were looking at the gravitational behemoth that our entire galaxy orbits around. So, to come back to our original question, can we see a black hole? No, we can't see the singularity or anything inside the event horizon. That remains forever hidden from us. But we can see its profound and dramatic effects on everything around it. We see the brilliant light from its accretion disk. We see the colossal jets it spews across galaxies. We see how its gravity bends the light from distant stars. We hear the gravitational waves from their cosmic collisions. And most spectacularly, we have now seen its shadow silhouetted against the fiery backdrop of its own meal. In a way, this is even more profound than just seeing a dark spot. We're not just observing an object, we're observing the fundamental laws of physics being pushed to their absolute limits. We are witnessing space-time itself being twisted, torn, and swallowed. We see the story of a black hole written in the light, energy, and even the very fabric of space that surrounds it. And that story is far more luminous and exciting than a simple patch of black could ever be. The universe has a funny way of revealing its greatest secrets, not by showing them to us directly, but by letting us see the brilliant and beautiful chaos they leave in their wake. So, what do you think is the coolest way we've detected a black hole? The glowing jets, the gravitational lensing, the sound of them colliding, or the incredible image of its shadow? Let me know down in the comments. Thank you so much for joining me on this cosmic quest today. If you enjoyed this journey into the dark heart of the universe, please give this video a thumbs up, subscribe to the channel, and make sure you hit that notification bell so you don't miss our next exploration. Thanks for watching, and as always, keep looking up.